Yeah, okay, there's no words. Anyway, you keep the time for me. Victor, thank you very much for being here. I would like to thank the organizers and especially Victor for the invitation. I am based in France, actually, not very far from here. At the moment, I'm at the Jussier campus, just 10 minutes away, but I'm actually working at the University of Montpellier. And I'll try to talk and give you a bit of an overview on work that we have been doing with a number of people, quite a lot of collaborators on tipping points and early warnings. And actually, preparing this talk, okay, it works. So preparing this talk the other day, I was just before going to bed, like just a few days ago, I saw this on the headlines of the Guardian. And I don't know if you have noticed that this is based on a commentary by Lenton and colleagues. And it was very interesting to see this news. They're coming more and more often on a newspaper. When I checked, that was like late in the evening. When I checked the next day in the morning, there was not anymore in the headlines. So maybe it's more for the late reading news guys. They get more the environmental related news. But I think that, or it looks like, and I think most of the people in this room will agree that this type of conversation becomes even more common during these days. But anyway, I'm not a climate scientist and I'm not a mathematician. I am an ecologist, or more correctly, I'm a desk ecologist. And in ecology, don't know what happened there. I can try again, maybe. Oh, really? Oh, no, it worked. Okay, thanks. And in ecology, we're fascinating with the concept of stability. Actually, we love stability. We love to study it. And we'd like to give the definitions about what stability is. And we want to know what factors affect the stability of ecological systems. Also, we are very much intrigued of how we can measure stability, how we can go out in our systems and measure if a system is stable or not. And in particular, a question that is more intriguing to me is like, what happens when stability is lost? While what I mean with that is like, usually if we think that this is the state of our system and there's some type of parameter, usually a stress, you can have, like a linear response to your system. So maybe stability is lost or not, but nothing really happens to the state of your ecosystem. In other cases, things may become a little bit more peculiar, where you have that more of a linear response to the state of your system. But there are occasionally cases where, and we have some examples from earlier talks, where the stress is increasing and then you are reaching a point here, this threshold, that here I would call a tipping point, where your system is going to respond in a very abrupt way, leaving this state, going to a different alternative or multiple alternative states, doesn't really matter. And this is the type of tipping points or this type of behavior that we are very much intrigued to understand in ecological systems, but not only. Because actually it's a bigger, I think, a bigger phenomenon on trying to understand what will happen under ongoing environmental stress and change. And a classical example that we start looking at this type of transitions in ecology is the example of shallow lakes. With the idea that you can have lakes that can be in two contrasting alternative states, either a turbid state or a clear water state. And actually what is driving this type of dynamics in lakes is the existence of strong positive feedbacks. And in particular in the lakes, we have this strong competition between macrophytes, that's the aquatic vegetation that lives within a lake, and algae. Algae, that's the microscopic phytoplankton that's also a plant, but lives suspended in the water column. And the idea is that the macrophytes have a strong negative effect on the algae by allelopathy, extracting toxic substances that don't let the algae grow, or by retaining nutrients from their water column, or by creating refuge for predators that go and eat the algae. And on the other hand, when algae are more abundant, they don't let the macrophytes grow because they start shading them. Macrophytes are plants that need the light to grow, and they can dominate the lake. And the thing is that in these systems, when you start increasing nutrient loading, when you're releasing the nutrient limitation from the algae, you start breaking down this positive feedback that it will not anymore work in favor for the macrophytes, but it will start working in favor for the algae. And eventually, your lake can shift from a clear water to a turbid water state. And there are examples of these types of transitions due to eutrophication in a lot of aquatic systems. But what is interesting, or what is more interesting, at least for me, is like we can see this type of changes and abrupt changes at different levels of ecological organization. We have population collapses. This is the example of the Atlantic cod in the early 90s. We can go up to bigger scales. We had examples already. So it was like in the past, more than 5,000 years ago, you had the Sahel, like a whole biome shifting from more of a savanna-like to a desert-like ecosystem. And even at much higher scales, and that's, I guess, part of what this workshop is also about, the climate has never been stable. We have these periods of very strong changes, like this is the example of the collapse of the thermal line circulation, that more than 10, 11,000 years ago, the temperature dropped because that circulation that brings warm water from the Gulf of Mexico stopped. And as a result, the climate in the North Europe at least became much colder than we know it today. And things have relapsed. But of course, if we would be able to understand this type of abrupt changes, of strong changes that are generally perhaps are put in a circle of tipping points, and we can come back to this, the question is whether we can try to understand what is driving them and whether we can be able to detect them. And that's mostly what, as I said, I'm interested in. I'm looking on this, on this broader issue of understanding resilience of these systems and possibilities of detecting this loss of resilience that can ultimately lead, perhaps, to tipping point abrupt responses. So that's what I want to talk to you about today, a little bit about an overview of methods, how we are approaching this problem. Again, we're starting from ecology, but the things that I'm going to describe about it's generally about systems theory. And the other thing is I'm going to show you at least some examples of application of how you can use these approaches to more loosely quantify these metrics to say something about the resilience of your system. So to start with, we're going back to the example of the lakes, for which we can write very simple mathematical models that describe this type of transition. And as before, here we have the environmental conditions, in particular the nutrient loading, where here we have the state of our ecosystem, the amount of macrophytes in the lake. And these two black lines here represent the two alternative states in your system, which means that for the same conditions, either you are on this branch, on the clear water, happy lake, or on this lower branch, on the turbid water, the lake that it's in your undesired, from a human perspective, state. And as we're changing environmental conditions,
I'm sorry, it really irritates me because the attribute catastrophic doesn't have any meaning in mathematics. It's a bifurcation. It's just it's just a more exciting name for a bifurcation, which is known since long time, 300 and some years ago.
Absolutely.
Okay?
I completely agree with you.
The Guardian can do with what one author of the study said, whatever they want. But in this institute, we do not refer to catastrophic bifurcations.
Okay, then
something else which is called catastrophes, which is bifurcations in 2 dimensions. Anyhow, sorry, just...
Point taken. As I said, I'm not a mathematician. This is how I have seen it also in mathematical text being described, this type of saddle node bifurcations. And okay, the catastrophe, okay, if just to be friends for this next 45 minutes, the catastrophe, it's more of the idea that you have this abruptness in the response of your system, this discontinuity. But I agree with you, it's a bifurcation, and it's what we have been calling tipping points in most of these cases.
Just in order to attract attention.
Yeah. Excuse me, Michael, but in ecological community, I think that that's of course different terminology. So
No, you can. We can continue, but I'm not going to argue. You know better the maths than me. I'm just saying we're using this concept, and we're using this concept to describe our system that follows these characteristics. That you can have these abrupt changes, these discontinuities at this bifurcation point. Yeah, if you want to call it a local bifurcation point, that perhaps it's catastrophic or not. We can argue about the saddle node or a fold bifurcation, or as you like, you want to call it. And from which your system shifts to this turbid water state. Now, the interesting thing with these types of systems, of course, is that you have this hysteretic phenomenon, which means that if you want to reverse your system back to its previous state, you can't do it at the same level of conditions at which your system shifted, but you would need to reduce neutral loading to a much lower levels, which for some cases, at least for ecological systems, it's completely impossible, which actually means that if you have systems that behave like this, they will be completely irreversible to manage. So, exactly, so it's this amount, the hysteresis could mean irreversibility for a lot of systems. So now what we define as resilience is this distance between this continuous line, which represents the equilibrium, and this dotted line, which represents the boundary between these alternative equilibria. And you see the distance between this line represents the space that you can have a disturbance in your system before you can shift to this alternative state. As you come closer, as you are moving and your conditions, the stress in your system increases, and you're coming closer to the bifurcation, you see that this distance becomes less.
So, Vasilis, if we turn into a potential, like,
yeah, so
when it just, your resilience is in depth of this potential.
Exactly. So the resilience of the potential of your landscape starts to decrease. It becomes more shallow, or another way, the distance to the threshold, to this threshold becomes lower. So that's why we will call that your system is losing resilience, comes closer to the tipping point, has a higher risk of shifting to this alternative state. So now the question for us is like, if this type of behavior we can see it in a variety of systems, and we can have models that can describe this type of behavior for a variety of systems, whether we can have some kind of idea of how we can detect tipping points in advance. This decreasing in resilience and this approach to these instabilities, to these bifurcations. So it seems that it's possible to do that just by taking into account the existence of a very generic phenomenon close to these bifurcation points. The fact that systems, when they approach these instabilities, becoming slower and slower in responding from perturbation, their dynamics become increasingly slower. And of course, this is not new, as it was mentioned before. This is known in mathematics and in the engineering literature, both in the work of Tom, of structural stability, and you see there, like already in the 80s, there were these ideas that we can use the patterns derived from the dynamics of your system to say something about its stability. So we're using these ideas, and if we go back to our original system, we compare one situation when we are far and when we are close to the tipping point, and we just monitor the dynamics of our systems, we can see three basic things happening. The first is that if we perform a disturbance at some point in our system, the system will, since we have now a global unique equilibrium, the system will return back to its original state. But you see that if you are closer to the tipping point, the system, because of that slowing down phenomenon, the system takes longer to recover. So the first indicator we can have that the system is losing stability and is losing resilience is that the recovery time in your system after disturbance is increasing. The second thing is that if we wouldn't have this possibility to perform this experiment, but we will just monitoring the dynamics of your system in the presence of environmental stochasticity, you will see that the signature is very different. And basically that you see that closer to the tipping point, the variability in the system is increasing. And the third thing is basically the same information, but presented in a different way. Like you see that your system starts to look more and more like its past. So here you see that if you plot today versus tomorrow, you have a very low correlation between the subsequent states of your system. Whereas if you are closer to the tipping point, you see that today starts to look more and more like tomorrow. So in other words, we can quantify this as an increase in autocorrelation in your system. So we have these three potential signatures that we can use as indicators to tell us something about the changes in stability and potential of existence of tipping points in our systems. So we can discriminate these two, or we discriminate these two in two categories, we can say. And the first one, as I already started to say before, is they require the existence of an experiment. So they're more like direct measures. It's more like that you're trying to measure the stability of your system by disturbing it. And these disturbance recovery experiments have a very long history in ecology, like we're doing it all the time, and maybe in other disciplines. So I'll give you an example of how we try to do this. We used phytoplankton population in the lab. And phytoplankton, as I said before, is like these small plants that grow in the water. And the thing is that they need light to grow. However, if you are exposing them to very high light stress, they don't grow anymore because their photosynthetic equipment becomes photoinhibited. Actually, they're just taking too much light to grow. But what they also do at the same time is like they can sustain higher levels of stress because they can clump together. And by clumping together, they create shading. So they create a positive feedback in favor for their own growth by creating shading and being able to grow at values of light that before they wouldn't grow at all. So we use this knowledge from these systems to perform an experiment, and I would say that it's more my colleagues back in the Netherlands who did this experiment than me, where we increased this light. Here we have increase in light intensity, and here we have a metric that represents the density of the population in the chemostat. That's where we were growing them. It's like a little device, it's a glass device in the lab that we were forcing them by increasing light. So if you follow the black circles, that's the experiment where we increase light. Whereas if you follow the white circles, that's the experiment where we reduce light. And you see this kind of hysteretic effect. And also what was interesting for us, you see that there's a point where they're growing well, but above some light intensity, they start to growing less well until the point that actually they almost collapse. So for us, that was like a good experimental system to test our hypothesis, whether if we were going along this direction and we were doing these recovery disturbance experiments, we will see that the population is slower the more closer we are to this threshold where they will start not to grow as well. So this is the same experiment basically, but now we have not light, but we have time. And a long time, I'm missing a line here, the light was increasing very slowly. And you see we were here tracking the population using very sensitive data loggers, capturing like light, how much light is passing through the glass to give an estimate of the population density. And at different times, we performed these disturbance experiments, these little P1 to P6. So we disturbed by removing a part of the population, and then we saw the population bouncing back. And we measured, for instance, the recovery rate of that population. And what we find, following what we would expect to see, is the higher the light, the lower the rate of recovery. So it took them longer for them to respond, so they were becoming more slower because of that loss of stability, because of that closer approach to this point where they were start collapsing. So this is about the first part, but of course in most cases the problem is that we can't perform these direct experiments. Like, I mean, we can do it in the lab, but we can't do it actually in the field. Of course, in that case, a nice analog sometimes we can do like the space for time substitution that you mentioned before. We can perhaps use natural disturbances that somehow we can normalize for different systems and then start to compare to get an idea of whether systems are like measuring the recovery after a fire in a forest, for instance. But in most cases, we don't. So we have to resort more to these indirect measures of resilience, like just taking a signal, taking a pattern out of your system and trying to give some measurement that will give some sense to changes in variance and autocorrelation. So for this, we need long-term monitored data. And in ecology, we don't have them yet, but things are changing rapidly. And we will see more examples of this in the future. So we went back to the climate, to our climate colleagues, where there are more data available to do this and also more knowledge. So we go back to this thermal line circulation example, and this is work that also we did together with Victor, where Victor actually provide us first with some model simulated output. So this is a model simulated output from intermediate climate complexity models, where actually represent the dynamics of the thermal line circulation. And you see that as the system is changing due to first water forcing, there is a point, a bifurcation point, where you'll have this saddle node bifurcation, and then the circulation will stop. So we were not interested in what happens here. We're interested in just analyzing the signal that we got from here. And the way we did it, very simplistically, like we used half the size of this window of data, and within this window we measured autocorrelation of that time series. And we plotted it here. And then we moved this window one time step ahead in time, leaving one time step at the beginning of the time series. And as we were moving this window closer to this bifurcation, we were just tracking at the same time and measuring autocorrelation. As if we would be a manager, and we will have getting this signal from our system, and we will try to see how the dynamics start to look like. And what we saw was that the autocorrelation was rising, which means that the dynamics start to look more and more like before. Maybe you will say this is the trend. This was done on a detrended time series.
I thought it's Hermann Held who contributed to that.
Well, you also contributed too. Yeah, okay, but you contributed too in this paper in general. So, this was the simulation, the model data, and also we used the example of of empirical data for paleoclimate proxies. And basically, it's the same. We did the same analysis, but now on an empirical data set. And this is the signal that we took. And you see that we found also a positive trend in autocorrelation prior to this transition point. And actually, we repeated this for 8 different types of past climatic shifts, and we found similar signatures, which overall for us was like a demonstration that, yes, it is possible to find ways to measure these changes in these signals, like autocorrelation variance, as well as recovery time that can be used as proxies of stability and potential tipping points in our systems. So we were happy that we could, at least as a proof of principle, could show that these ideas have some merit. But of course, there is a lot of work to be done and has been done. So one of the things, for instance, is that we're still having a lot of theoretical challenges, because what I have been focusing my talk is more talking about this very particular type of saddle node bifurcations. But you see that, for instance, the phenomenon of critical slowing down that I'm talking about also corresponds to different types of bifurcations that are not necessarily saddle node abrupt bifurcations, but can be more of a continuous nature. So there is work that we show that actually, yeah, this is a more generic phenomenon. So these warnings that I'm telling you about are not necessarily specific to tipping point responses. But on the other hand, we also have different cases of transitions that they are not necessarily accompanied with critical slowing down, but they still have the element of tipping, the element of surprise, for which we don't have very good clues of what we're going to use as warning signals. The other problem that I mentioned already is the practical implementation of these signals. Basically, we need good data. That means that they are low in measurement error, that we have good resolution, we don't have gaps. We don't yet have this type of data available, and that's why there is work that shows that you have difficulties in applying this type of approaches. But I'm on the optimistic side, because more data are coming. There is better long-term monitoring data. We have remote sensing data. And so the data will be there. And for this, we need to be prepared. And here I want to show you that we have gone a long way to create a series of methods and indicators to try to quantify these signals with, going over statistical hurdles and, multiple analyses. So we have quite a big list of things that we can do, that going on the direction of detecting this type instabilities. And I talked for time, but also we can also do it in space, because basically we can also have spatial slowing down. So slowing down in space and other more specific indicators that come into specific patterns that was presented in the morning. So we have a lot of tools, and we are, as I said, I'm more optimistic that we will have the data to test more and more of this hypothesis, at least for ecology. But not only because I have to say that the ecology and climate, there is also a lot of work that has been done using this type of approaches for climate. But so they have dominated the field of this application. But also I have to say that there are other types of systems that they are using similar ideas, because again, as I said at the beginning, we're talking about a system level property. So this is a little bit of an overview of like the methods work that, as I said, we have done with a lot of colleagues. I'm very grateful. And we're trying to see that, look, we can have some type of methods that we can monitor and changes in systems to say something about its resilience and potentially its proximity to a tipping point. That's what we would call an early warning. But don't take it literally. It's not really an early warning. It's more like it's more of an indicator. So the second part I want to talk about again, this more nuanced approach. Like, okay, more generally, we can use that more generally to say something about resilience and how can we apply these things. So one example, sorry, I'll stick with some ecological examples, at least for now. It's about pollinators. So plant pollinators interactions, plant pollinator communities. There is a crisis for loss of pollination. You have heard about the decrease in populations of insects. So there is a bit more generally a biodiversity crisis. And so, the question that we were looking at was whether, like if you would be able to have and to be measuring a community of plant and pollinators, whether you could be able to say something about their loss of resilience on understanding, for instance, or identifying, for instance, which species you should be trying to protect, prioritize, and stuff like this. So plant pollinator communities are, I guess you not know, but okay, these are the plants and these are the pollinators. So the plants are providing nectar to the pollinators, to the insects mostly, also it can be birds. And the pollinators are actually pollinating the plants. So you have this positive interaction between the two compartments. And usually you have this type of structure. You have this, what you call the bipartite network, where you have the animals and the plants interacting in specific ways. The problem with this is that we don't have information, actual abundances. It's difficult to track abundances of individual populations of these species. But what we do have is their interactions. So so this is a true plant pollinator network from the south of America. Here you have plants and pollinators, and every dot represents an interaction between plants and pollinators. So we have information about their network. And at least what we can do for the beginning is like we can try to use mathematical models that describe the dynamics of these populations. And that's what we did in this exercise. We analyzed these communities, the dynamics of these communities using models similar to what Benny was talking about of Lotka-Volterra type of dynamics. And under a scenario of increasing stress, under a scenario where where the community will be stressed and resulting in loss of biodiversity. So to exemplify this, so here every line would be the population of each species in that community. And on the x-axis, we will have a stressor that, for instance, will decrease that positive interaction between the plants and the pollinators. And what you see is like if you take the real network of interaction, you plug it into a model, you see there is a point where you stress them too much, you have a sequence, a cascading of tipping events, of groups of species getting extinct from the system. So our question is like, if we had information only on this part, where you would say that something is happening, because the abundances are decreasing, but you wouldn't be necessarily know that that would mean that your species are going to get extinct. If we have information only by monitoring these species, could we make some type of ranking of which species would go first, die first, so it would be more vulnerable? So analyzing that, we get a picture like this, where here I have ranked the species in terms of extinction sequence. So here are every node is a species of plants, pollinators, and plants. And I have ranked them in the extinction sequence. So here are the ones who died last, and here are the ones who died first. And the colors represent species that died at the same time together, went extinct as a group at the same time together. And what you see, if it's possible, I don't know, you see that here with grayscale is the change in variability of a species at the beginning of the experiment, just before we had the first extinction in the community. And what you see that indeed, as we would expect, that if you have species who had the strongest change in variability, this would be the species that would get first extinct. So the ones who would be less stable and more close to their tipping towards extinction, compared to species that they were had a smaller change in variability. So in that way, we could use that information. If we had this information for ecological populations, we could rank them and give some prioritization of which species are more resilient or less resilient. But we don't have this information yet. So we can do something similar for going back to the climate. And in this case, we can ask something similar, but using, climate projections. And usually what we have been, or at least what I have been seeing mostly, is how the average temperature would look like in the future based on these RCP scenarios. Like this is a picture like this. But here we were also interested to see how would variability look in the future, and not just how variability would look in the future, but how variability will change in the future. Because, as I said before, like an increase in variability or changes in variability could be seen as proxies of system instability. So maybe I'm not very clear what we did, but maybe this will help it clear it out. So what we were interested in is to estimate changes in variability in future temperatures at the global scale using predictions of climate models. And the idea, as I said, was to see whether these changes in temperature variability can show us hotspots of climate sensitivity / resilience in the future. So whether there are some places at the global scale based on the model predictions that will show a higher change in variability, and maybe these places would be more sensitive in terms of their system resilience. But not only, because the way we want to see it is changes in temperature variability could mean, for instance, that here you have your historical average, right? And maybe higher variability would mean in the future that you are living in a world like this. Or also it can mean that you are living in a world like this. So these two scenarios will give you, will show you an increase in variability in the future, but here also you will have this longer memory, which reminds of these slowing down dynamics that I presented to you before. And for us, I mean, it's interesting from the climate perspective, per se, for instance, to identify these areas, but for us it's more also interesting from the ecosystem perspective, because you can imagine that if you have ecosystems that are going to be exposed to this type of future scenarios of variability, not just an increase in the mean, but actually living in a more variable world that would look like this, or even worse like this, then you can have implications in terms of the physiological response of the species, increased risk of extinction, the functioning of whole ecosystems. So it served for us two angles. One, to see whether, looking from the perspective of the climate, you'll have higher sensitivity, which would mean something about the stability of the climate system itself, but also in terms of how this would cascade in different types of systems, like ecological systems or even human systems. So this, of course, work I'm going to talk about that was led by Sebastian Battiani, who also was with Victor in the past. And I think he's now back in Hamburg, for those who don't know. So you can meet up with him again. Where we used, as I said, model output, for instance, from a specific grid cell. This would be the model output. We detrended the data, and we have what we did was to compare what's the relative change in variability when we looked at the end of the projection, the 30 last years of the projections compared to the beginning of of the model fitted on the historical data. So we want to see relatively change in variability at in the projected temperatures compared to what has been, was at the beginning of the record. And we didn't do it for one model output, but these details, okay, to be honest, don't really understand, but we use it for 37 different models that generate these projections. And what we found, again, I will show you a global map of relative changes in variability based on these model projections. That would look like this. So if you have red, you will see that you will have an increase in variability, and the darker the red, the higher the increase, whereas if you have blue, you will have a decrease in variability, which is also very interesting and perhaps something that it would be less expected, at least for people who are not into climate like me. So you will see a lot of heterogeneity. I'm presenting you averages for the whole year. We also see differences across seasons, but we don't have to go into that. But basically the point was that there was a lot of heterogeneity, and there was also a lot of disagreement between the models. So here the hatched areas represent the areas where at least 30 of the 37 model outputs we used gave us the same result, the same trend. So that means that only in a way more significant or more reliable estimates would be the ones where we had the highest model disagreement. And you see the areas that were or will be more negatively affected, assuming that increased variability is a proxy of lower resilience and higher sensitivity, are the usual suspects, right? In Amazonia, in the Sahel, South Africa, and Southeast Asia and Australia. What was interesting with this map also was that we could manage to connect it to some socio-ecological or actually better socio-economic features of this area. So what we did was we tried to see what is the relationship between the projected changes in variability versus the GDP, versus the economic power of the countries where this, of different countries. So in a way, how much each country would be affected depending on its economic capacity. And again, what we found was like basically confirming the usual climate injustice conclusion. So you see that, so the positive values here, the ones who have increased variability, that will be the worst off. Whereas here you have the decrease in variability, maybe that means good news. And you see the developing world, or most of the developing world, actually will based on what we found, we will experience a decrease in variability, whereas most of the undeveloped world will also suffer a higher increase in variability. Yeah, for people who are from France, France was somewhere here, so in the good region. So to summarize from this, basically, I want to show you that we can use these ideas, these relative changes in these very, in these indicators, in these indices, also in a more broader way to try to rank and resilience between different systems or different species or different sites, like so now with the plant pollinator community or with the climate system. And in this way, by doing this ranking, we can get an idea of perhaps identifying areas or species that could be more vulnerable, more sensitive, and it can be like more hotspots for conservation or for our attention. And I think I would like to thank my co-authors that helped me with this, and of course you for your attention.
Thank you very much.
Vasilis, for bringing us in the exciting world of early warnings and tipping points. And yeah, we apologize, Michael, for bringing ecological understanding.
I'll explain myself, but apologize.
Sure. At first, questions? Or you want to do it immediately?
I mean, I'm a participant and somewhat of one of the instigators of a European project called TIPES, tipping points in the Earth system. So clearly tipping points have been very helpful in attracting the attention of the broader community to bifurcations. And they also have a more precise mathematical meaning in the context of so-called non-autonomous and random dynamical systems, where you have, instead of coefficients enforcing independent of time, you have them dependent of time. There you can do things. But thank you really for a very good talk. And it was just the catastrophic bifurcations which got my goat. So,
yeah, and just during the lunch, you just explained us that 3 weeks ago or a month ago you had a TP's kickoff meeting exactly in this room, right? So it's
yeah.
okay.
So,
Nice.
but now that you don't call it anymore catastrophic bifurcations.
Well, if you, it's just, don't overdo the rhetoric. That's, there's a rhetorical aspect which comes from the social sciences and helps maybe, raising money. There's another thing that's a scientific part. So don't mix the two.
Yeah, I mean,
bifurcations is enough. Catastrophic bifurcations, it's too much of a good
so how do you call a bifurcation that has this discontinuity aspect?
A bifurcation.
Yeah, but
That's
if
what
you
a
want,
bifurcation is.
yeah, but bifurcations are transcritical is also bifurcation, but it has no discontinuity.
Well, say something else.
So, or a Hopf one. So how do you call these ones that are?
Look, the thing is that towards the end you had some very good references about, moderating the enthusiasm for these warning signals. I mean, you had this Venn diagram with, different things happening. It's clear that there is a fixation of the ecological community in particular on saddle node bifurcations, okay, for which all those things are true. But I wanted to talk about resilience because I recently directed a PhD thesis on resilience with a very, very bright young man, Célian Collomb, who is now at IASA, in Luxembourg, near Schloss Luxembourg, near Vienna. And the definition of resilience is a really very difficult thing. Again, in the simple case of so-called gradient systems that have a potential, in other words, in one dimension, you always have a potential, but in several dimensions, some systems are gradient systems, others are not. You can define the resilience as a depth of the potential well. But in other cases, that is not the potential doesn't exist, you can't define it, and it's very difficult. There are very different definitions. So, please look at the introductory chapter of the PhD thesis of Célian Collomb, which has the word resilience in the title.
Yeah, thanks for this nice talk. It's very illustrative. Now, the last example with the climate variability, I can see that it points into the direction of the question of resilience of society. Because if we have large variability in a poor country, then the societal or political resilience is a danger, which might have little to do with tipping points. Okay, you can then say it might transfer into a social or political instability, but that has still to be defined. No? Because if you go to this slide, it shows that the Sahelian stuff is really a danger, but I think it's because of the political stability. And you also mentioned at the beginning that about the Saharan collapse, which, you can infer from one time series, from the time series that Peter Domenico provided, but that's only a single time series. And you cited Sebastian Battiani, he did a PhD with me, showing that for the Sahara you cannot show the early warning system does not apply, simply because it's heterogeneous. And if you have a heterogeneous system, you have many time series, and you have little subsystems which affect each other, such that all of a sudden there might be an early warning, but it's misleading because it doesn't happen anything, or there is all of a sudden something, And there is no early warning, simply because for this interaction. And I assume that in most cases, if it comes to climate, if you have a heterogeneous system, spatially heterogeneous, then it might be much more difficult to get something out. No? And so I like the way that you have a clearly defined single systems, then you can do all the applications. No?
I completely agree.
Yeah,
If I may, I showed you the more clear examples to get the idea, because we have worked a lot also, as you mentioned the word of Sebastian, on what's the effect of spatial heterogeneity in this system. And then you see these effects that, of course, the signals are stronger when you have a well-defined homogeneous system. Once you have, like with the species, once you have more species, every species don't show you the same direction. They can tell you something locally about their own fate or its own, like a specific habitat or a specific space in the Sahara, for instance, but not something about the whole system.
So my question would be then is there any possibility in this heterogeneous system, with a number of systems which affect each other, to come up with any early warning system, or does the early warning system doesn't make any sense anymore?
I think it makes sense locally. So
yeah, but locally is really the problem, because if you have a tipping at one site, it can happen because of an induced tipping or by another site. And if you look just at one side, then you don't see the other side, and you can have tipping without any early warning, and vice versa. It looks like something, but nothing is happening. So.
But you will, at least for the community of species, which is something analogous, it's like different species that. So some of these species go extinct not because they are suffering the most, but because, for instance, their resource is going to die. So you will see something is happening. You will not be able to infer why. So you will get a signal, but not necessarily you will be able to infer why that species, for instance, or that site is showing higher variability. Like showing this signal, but it will give you at least an indication, like that something is happening. And of course, it depends on the system. And I agree with you. We're not in the position to get a very generic and universal behavior, because they will be also system specific. So you have to interpret these signals. Always in the context of your system. Like if, for instance, if you know the interactions between or if you know the spatial heterogeneity in your landscape. And if I may, for your first comment, like it's more interesting in that story, the effect of that climate sensitivity, how it will affect other things. Because what we're trying to do now, we want to make for every site that we know or we have an indication of the projected climate variability, we want to compare this map to the map of species extinction risk that we know now. So what we're trying to do is, like we want to at least speculate of, look, these species who are now, for instance, endangered, are going to, if we project where they live, we'll say they're going to live in areas that will become more climatically variable in the future, which perhaps, it's a hypothesis, will increase the risk on the species. And it's the same idea we're thinking here with the countries. So the countries that are more vulnerable because of instabilities, they will be perhaps more sensitive if they live also in an area where in the future we'll have more climatic variability.
Okay, thanks.
Great talk, Vasilis. That was really fun. I want to start with a comment about your catastrophe issue. I agree with you mathematically, but I think that to point the finger at social scientists and say that they like to use emotive language, I reckon a lot of this stuff came from mathematicians. I mean, nonlinear dynamics is full of people who love to use catastrophic terms and are good at self-marketing. Anyway, I just want to ask you a question about the toolbox of indicators.
Yeah.
The more you have, the more the chance that one of them will be of, if they all have a probability of false positives, then the chances of having no false positives will become zero when you have 100 different metrics you're running, right?
Yeah.
How do you deal with the fact that you're offering 20, 30 metrics people can run? I guess the more you offer, the more chances you'll get these false alarms.
Well, most of them are actually quantifying the same thing in different ways. So there are truly they are not 20 as they look there on the figures. It's more like a different visualization or a different estimation of the same thing. So now if you see the literature, you see also that we're putting more trust in 3 or 4 of them. So we're looking basically at 3 or 4 things. But indeed, the idea is that, and again, of course, first you want to see that something is working. But now, of course, the beauty would be the reliability will increase if you also using these integrated signals, using multiple of these indicators at once, and they show the same thing. So now we're also using, kind of weighted averages of all of these indicators, because it seems so far it's quite hard to have all of these indicators, like giving you exactly the same information, giving you the right true positive. So you try more, and you either you look at them individually or you create a weighted average signal to. But again, this is just like inferring something from a pattern, right? How you're going to interpret it is a different story, and there is a lot of progress in like significance testing and null modeling, so like that you try to minimize that. Okay, you found something, but that doesn't mean anything until it passes that statistical test.
Okay, I found very interesting your plot about the hotspots, which you did by looking at variability in the far future in RCP 8.5, I believe. So you had this map of hotspot areas in the world. We did this sort of similar work 4 years ago or so, by looking actually only at the historical period. So comparing at the historical period. So comparing 1980 to 2010 with 1950 to 1980 or something like that, and looking actually at changes in multiple indicators. So the question there was, a hotspot is where you have many indicators of extremes, both of temperature and precipitation, changing at the same time. So not only one, but multiple. And the maps, I will show you, they coincide quite a lot.
And it was temperature or precipitation?
Both. We had indicators of temperature, precipitation, and the variations were interannual, so inside the same year, so seasonal variations basically. And so it's interesting that it actually there is some good correspondence actually.
So you mean that already from the observation of the historical record, they stayed, it's basically the same project?
And it applies to multiple indicators, not only one, not only variance of temperature. It applies to both temperature and precipitation. And actually, it's areas where many of these guys are changing at the same time. That's interesting.
You showed very early on the bifurcation, and then you had these arrows of resilience. I'm not sure how mathematical you were being there, but that just didn't look right to me. Surely it's the tipping point is the point at which once it goes beyond that, then it moves to the other point of the bifurcation. So measuring it to that dotted line between the 2 points doesn't strike me as the measure of resilience.
So this was the dotted line. So it has a potential. So that was like one stable state, and this is the alternative, right? And so if in that figure, so this distance basically it's this. Well, it depends. I think for me they're both. Because you need to go up and this direction to escape.
But imagine the right point, far more distance from the left one, but much flatter than any slight perturbation then kick the system.
It's the depth of the world.
There has to be the depth. Because, I mean, if it is very shallow, then you can easily kick it to the right or to the left. So it depends on
the Khamer's formula.
But they change at the same time, though. You see, in most of these.
The Khamer's formula for the time it will take to exit, subject to certain stochastic perturbations, only deals with the depth of the well, not with the width.
So if you like, this is a proxy of resilience.
No, I'm sorry, that's not a matter of interpretation, that's just wrong.
Yeah, Vasilis, I've seen these discussions a few times, and I'm now trying to teach master students about tipping points, about early warning signals, about these kind of phenomena. And I was wondering, is there a kind of so from an ecology perspective, well, you have a kind of background in there, and of course all the work done by Martin and so on, and in a way that sometimes clashes with mathematicians or so. And I was wondering, is there a kind of textbook for me, just that I can use to teach my students? So what kind of general work is there available which best shows, well, just to explain, let's say, in a way, resilience, and to explain...
Well, we're using the work of Buzz Holling from '73. That's like the seminal paper that Buzz, in a way, you know, is how much you can disturb a system before escaping. So in that dimension, you know, like how much you can move your state variable to cross that threshold to start moving to the other direction, for instance. And of course, there is the work of the book of Martin with a lot of illustrations of different systems for ecology, like from the Princeton University Press.
So still so it's still the work by Buzz, let's say, which is really the most important part, which should be taught to our students, you think? Well, it's very general.
Well, Stefan, let's continue over coffee break, because otherwise we just postpone everything too much. So I suggest discussion takes over the coffee break, and we convene here in half an hour, 10 minutes before 4. And thank you again, Vasilis, also for
starting
discussion.